Chapter 3 is dedicated to normal distribution, all about distribution or normal distribution, and a little bit of uniform distribution. So before we jump into this normal distribution, I want to introduce you the density curve. So the density curve is a smooth curve that you draw around your the histogram or any other graph, right? Why we do this, because it's, first of all, it's easy on the eye, right? And it's easier to calculate, to work with. So density curves have two characteristics. It is always on or above the horizontal axis. It's always above the x-axis, and has the area under the curve of exactly 1. Okay, so when you draw a curve, the area under the curve, that area under the curve is 100%, right? 100%, everything under the curve. Okay, all right, remember that. So here is a histogram. Okay, so before we jump into the normal curve, I want to introduce the uniform distribution, which is sometimes they call it the rectangular distribution. This is the simplest distribution of all continuous in all continuous variable. Okay, normal and then uniform are continuous variable, where binomial is discrete, considered discrete variable. If the range of a uniform random variable is from the number a to the number b, then the probability density function has a height of 1 over b minus a for all values from a to b. So what they mean by from a to b, so if you look at this picture right here, a will be the smallest value on the x-axis. So here a start at 0 and b start at 10. So that means your probability density function, short is PDF, is going to be 1 over b minus a. Well, b is 10, a is 0, so 1 over a. I'm sorry, b is 0. I'm sorry, b is 10, a is 0, so 1 over 10. 1 over 10. So that's the height, that's the y-axis. That's the height of the box. The width is 10. 10 minus 0 is 10, right? Okay. All right, let's answer some question. So if you take a look at this picture, this is the uniform distribution of a 10-mile bike path that they occur. Let's see. Oh, that's the exam, the location of an accident. Okay. Now, uniform distribution, the mean and the median is the same, right? Because half of it, that's your mean, right? It's also is your median, the middle values, right? The formulation represent the mean is expected value. E of x is expected value. When I say expected value, you should know that I'm talking about E of x, expected value. This is the same thing as mu. Does anyone remember what is mu? What does mu stand for? If you don't, it's fine. I'm just curious. Mu. Population mean, right? When population says sample mean is x bar, population mean is mu, right? So the mean is just the average of A and B, it's the average of A and B, right? So this formula right here. And the distribution, the name of the distribution is U A comma B. Okay, so if I give you a box and I ask you what is the distribution of this rectangular box, then you would answer in this form, right? Of course, you have to tell me what is value of A and what is the value of B, right? But the generic, it will be U A comma B. Okay, so for example, for this problem, the distribution is U with sample uniform. A is 0, B is 10. So U 0 comma 10. Okay, every picture has its name. Remember, I show you. I told you you should have a title for your graph. Same thing here. Density curves has a title too. Okay, let's answer some question. Based on the model, what is the expected miles that the accident may occur on a 10-mile bypass? PAP, I'm sorry, PAP. Provide appropriate symbol and value in units. Okay. Expected value. Expected value is E of X, right? That's what they're asking you. They're asking you to calculate this formula. That's expected value. So provided appropriate symbol and units. So it's going to be E of X equal mu. Expected value is the same thing as population mean. In this case, it will be A plus B divided by 2. A0, B is 10 divided by 2, so 5. What is the unit? Oops, I'm so sorry. I keep touching the thing on the side. What is the unit? What's 5 represent?
Miles.
Miles. Thank you, Sean. Miles. Don't let one person do all the work. I want to hear other people talk too. So far so good. That's just applying formula, right? What is the probability that the accident occurred within 0 mile and 2 mile? So 0 between 0 and 2. Between 0 and 2. Let me draw the boundary between 0 and 2. By the way, when you hear probability, in terms of density curve, it's the same thing as area. Okay, like area under the curve. Okay, here is a box. So the area is just width times height, right? So what is the width between 0 and 2? What is the width? 2, right? And what is the height? I already answered the width, so you can answer the height. Maybe I'll call. Megan, are you out there?
Yeah.
What is the height of this distribution or of this box?
Would it be 0.10?
Why is it 0.10?
So that's how far the box goes.
Oh, okay. That's how far the
That's
box goes.
how tall it is.
But if on the exam, if I don't give you the tick mark, then how would you know?
You wouldn't?
If
I don't know. I don't know the answer.
I don't give you the tick mark, which I won't on the exam, I'm not gonna give you a tick mark. How do you guys know it's 1/10? Anyone want to help? You won't see tick mark on the exam. You have to figure it out on your own, which is I mentioned earlier, which is this one, right? This one. Remember the probability density function right here? Let me highlight it here. So right here has the height of 1 over b minus a, right? So as long as you know what a and what's b, you can figure it out the height yourself. That's why I say I'm not going to give you the tick mark. All right, so the height is 1 over 10 and the width is 2. So the probability is just width times height. Width times height. 2 times 1 over 10, which is 1 over 5, which is 0.2, 20%, right? Roughly, well, exactly 20%, 0.2 or 20%. Okay, now, this right here, that's English. Probability that accident occur within 0 mile and 2 mile. If I want to translate this into math, into statistic language, then this is what I'm gonna write. I'm gonna write probability is big P. Maybe I need some more space. I need some more space, so I'll go out here. Big P and then parentheses. Inside the parentheses, that's your random variable. My random variable is always denote X. And X is between what? Between 0 and 2, right? So that's why they call random variables. It's jumping between 0 and 2. 0 and 2. If you forget, if you do 0 less than X, less than 2, that's fine. If you don't have the equal thing underneath, that's fine. It's a continuous random variable. It doesn't matter at the point because if at X equals 0 and X equals 2, that's just a line, right? And the area of a line is 0, right? So it doesn't matter. Yeah, that's how you translate from English to stat language, okay? And I do expect you to show me that part. Right? If I say, what is the probability of something between something, then you should say P of that number, X between that two numbers, all right? Last one, what is the probability that accident occurred over a 6-mile path? Probability that the accident occurred over 6-mile path, over 6 miles. So here's 6 mile, here is 6 mile, over 6 mile. Let me draw, oops, too big. They're over 6 mile. That's everything right here, over 6 mile, right, over. So they want you to find what is the area of that box, right? So same thing, since the rectangular is just width times height, so width here is 10 minus 6 is 4, and the height is still the same, right? So 4 is the width and height is 1 over 10. 4 over 10, if you reduce, that will be 2 over 5. Can someone tell me how do I translate this into stat words, into stat language? I did it before. I did it this one. It's very similar. Sean, you want to give it a shot?
Would it be P and then the parentheses and then yeah, I don't know.
There's X, right?
Yeah, X
and then it's gonna be then 6, right?
right.
Is it greater than X is greater than 6 or less than 6?
Less than 6.
Over 6 mile.
Okay, so greater than.
Greater, right? So X here is could be what? It could be 6.1, 6.2, right? It could be any number between what? Between 6 and 10, right?
Hmm.
Yeah, that's what X means. That's what they call X is a random variable. It's random, right? It could be any of those values between 6 and 10. Okay, so 2 divided by 5 is roughly 0.4. Thank you, Sean. Roughly 40%. So this right here, this area right here is 40%. If that's 40%, how much would this be? How much on the other side? Maybe I say the blue part. How much is the blue part?
%60.
Yep, 60%, right? Because under the curve is the area is 1, right? So the blue part will be 60%. 60%. All right, follow-up question. What percentile does the value of 6 mile correspond to for this distribution? So what they're asking you is at 6 mile, what percentile is corresponding to? Is it 60 or 40? What's percentile mean? It's the percentage of an area of the percentage of what is that percent? It's the percentage at or below, right? At or below. So at 6 at or below is what? At 60% or below 60%, right? So at 6, right there at 6 mile, the percentile corresponding to the value 6 is 60%. 60%, right? 60%. If I ask you what is the so if I ask, just hypothetically, if I ask you at 5, what is the percentile corresponding to at 5? 50%, right? 50%. So that's your median or your mean. So half here and half here. Okay. All right. That's it. We done with the uniform distribution. Now we're gonna jump to the normal distribution. For this slides, we already talked about this. When you have a symmetric curve, like the one in the middle, double M, symmetric, then the mean is equal to, maybe I'll use X bar. X bar, the mean is equal to, sample mean equal to the median, right? If the right skew, then the mean is larger than the median, which just makes sense, right? If it right skew, then you have a large value at the right tail of the data set, right? So when you average them out, the result is big, right? So it's bigger than the middle value. Left skew, then the mean is less than the median. Again, left skew, then you have a lot of tiny little small data point at the left tail. So when you average it up, it's small, right? The result is small. Okay, that's just review. That's just review. I don't care about the mode. Ignore the mode. Well, you don't have to know anything about the mode. Normal distributions. This is a very important distribution in statistics. So normal distribution represented by normal curve is completely described by given its mean mu and its standard deviation sigma. The reason you see a different notation here for the mean and a standard deviation because they talk about this population. Okay, so for population we use the simple mu for mean and a sigma. This one right here, it's the Greek letter sigma. So now sigma for standard deviation. Here is mu. Okay. The mean of the normal distribution is at the center of the symmetric normal curve. So it's right at the center, kind of like this. Right? It's at the center of the bell curve. The standard deviation sigma control the variability of the normal curve. That means when you have a large standard deviation, remember what is the definition of a standard deviation? Can someone remind me? We just did earlier in 2.7. What is the definition of a standard deviation? What does it measure?
It measures the spread of the data.
All right, thank you, Antoinette, very much. It's measure the spread, right? So the larger the standard deviation, the more spread, right? So here, if you on the left picture, if you see the standard deviation is large, then the normal curves kind of get fatter, right? It's get a little larger. On the right hand side, the standard deviation is small, so the bell curve it gets squeezed, becomes skinnier. So you have less variability, which when you have less variability, that means the data point in your data set is closer to the mean compared to the one on the left, right? The one on the left is the range, maybe the range, I'll give you just arbitrary example. Maybe the range is from 20, say 20 to 200. Over here, the range is 80 to 120. Right? So the value is closer to the mean. Here, the value is far away from the mean. So far, so good. Oh, I forgot to mention, I should have put another bullet point here. Remember in uniform distribution, I asked you to write the notation for distribution, U and then A comma B, right? Here is gonna be N, stand for normal, comma mu, I'm sorry, mu comma sigma. Well, what is mu and what sigma? It depends on each problem, right? Then you plug in the value for mu and then the value for sigma. Okay, empirical rule, we only use this if you have a normal shape. Your data set have a normal shape, have a bell curve shape. Anything other than that, you cannot use empirical rule. Okay, so we still on the normal things, on the normal distribution. But before we do that, let me talk about population and sample. So population versus sample. Population is, let's say, like, let me give you an example before I actually give you the definition. Say I wanna collect some information about STAT 220 students. I wanna know what is the proportion of STAT 220 at OU like pineapple on their pizza. Just some silly question. So one way I can do is I can go into each class and ask them, do you like pineapple on your pizza? And you tell me yes or no, right? And then I'll crank up some proportion. So how many percent, say out of 200 students, all STAT 220, the 200 student total, how many percent is like pineapple, how many percent don't like pineapple in their pizza? So that's one way to do it. I mean, go into classroom and ask for every single student, as long as they STAT 220 student, right? But that's take a lot of time. It's take a lot of time, and we don't have the manpower to do it, right? A lot of times populations and could get very large, like 1,000, right? The other way we can do it, instead of going and ask every single student, I can randomly pick a certain students. Say you're my student, so I pick you guys. You're gonna represent all of the STAT 220 students. And then I ask you the same question: do you like pineapple on your pizza? Right. So so the latter way that I do it is called sample survey. Right. I'm gonna use a sample. I randomly pick a few individuals from the population pool, and those individuals gonna represent the population. Okay. Why do we do it? Because it's less expensive, right? Less time consuming, right? When we don't need a lot of manpower to do it. So population is all the individuals you want information about. Right? Whatever information you want, their height, their weight, their academic standing, whatever you want, right? Sample is a portion from the population pool. So for example, if this bubble right here represent population, the little dot, red dot, is all STAT 220 students at OU. Right. So what I'm going to do is all of these people here, you in there, Sean, Bailey, Megan, Nirmal, you guys all in there, right? What I can do is I can randomly pick say 30 individual, right? 30 individuals from that red pool. Okay. So here, now I have a little sample pool, right? And I can work on this sample size to inference about the population. Okay. So the table. So let me draw you a table. Distinguish between population and sample. Population sample. 1, 2, 3. I think that's good enough. So here I have population, and here I have sample in blue. Now, all the numerical calculation in population is denote in Greek letter. Okay, denote in Greek letter, and we call them parameters. We call them parameter. Those are parameters of the population. All the calculation, all the numerical calculation in sample is called statistics. Maybe that's where the word statistic come from. That's what statistic people do. They take sample, and then they, based on that, they predict, right? Statistic. Okay, so what are the parameter of population? Well, we have the mean. We have the mean. We have right now. Well, so far we have mean. We have variance. We have standard deviation. Right. Can anyone remind me what is the notation for the population mean? Population mean.
Mu.
Mu. Thank you, Sean. Mu. Variance. I haven't talked about this, but standard deviation. Population standard deviation. Population standard deviation. Sigma, right? Sigma. So variance will be what? Variance will be, well, if standard deviation is sigma, then variance just what? Square of sigma, right? Square sigma. For sample, the mean is x bar. You all should know that. Variance is s squared. Remember the formula we used earlier in 2.7. And then standard deviation is the square root of variance, which is s. Okay, so those are simple. So when I mention these simple, you should know what they mean. Okay. For population, it's always Greek letter. It's that mysterious, because a lot of time we don't know what happened in the whole population, but we know the sample, right? We know about the sample. Okay, empirical rule. Now before I go here, we're gonna take a little break. Before we take a break, I'm gonna take attendance, and then we'll take a break. Okay. Just hang in there. All right. So empirical rules is we only use this if the distribution is bell curve or normal. Okay. For the bell-shaped curve, approximately 68% of the values fall within 1 standard deviation. So let me highlight something. So roughly 68% of the values fall within 1 standard deviation of the mean in either direction. Okay, 95% of the values fall within 2 standard deviation of the mean in either direction, and then 99.7% fall within 3 standard deviation of the mean in either direction. So what do these sentence means? I'll show you what that means in the picture. So here you have a normal curve. Remember, the middle value on the x-axis of the normal curve is the mean, right? So the normal is the mean. I'm gonna use parameter mu here. Within 68%, is 1 standard deviation. So that means from the mean to here, that's 1 sigma. Okay, standard deviation is sigma, is denote sigma, right? And over here on the left hand side, from the mean to the left is minus 1 sigma. Okay. So the points right here, so this point right here, so 2 little red dot here, that's mu, the distance is mu plus 1 sigma. Right? And then on the left hand side is mu minus 1, oops, I want to keep it in red, minus 1 sigma. That's what they meant by 68% of the values fall within 1 standard deviation from the mean on either side. Okay. And similarly, 95%, we have here 95% fall within 2 standard deviation. So 95%, where is it? 95% is from the mean to the second bar right there. So that's 2 sigma, right? And from here to here, that's minus 2 sigma. So that means this right here, the little blue dot there, that distance there from the mean is mu plus 2 sigma. And on the left hand side is mu minus 2 sigma. So you know the JIT, right? So if it 99, so that means now for 68%, what they mean by 68%, that means 68% under the curve. So all of that I highlight in red right there, because sometimes I cannot include everything. Oops, I went over. That right there is 68% of the normal curve, right? 95% is a lot. 95% is from here all the way, all of that to here. That's 95% of the data points. That's a lot too, right? And then the last one is 99.7. So even more. So 99.7 is from here, all of that, all the way to here. Almost cover the entire curve, right? Almost cover the entire curve. So 99.7, 3 standard deviation away from the, I meant to use green. Maybe I'll highlight in green. Right there, right? So from the mean all the way to the last column is 3 sigma, and over here is minus 3 sigma. So this down here, the distance on the green dot, the both 2 green dots, this is mu plus 3 sigma. And on the left hand side is mu minus 3 sigma. So in practice, from the standard deviation from -3 to 3, that's covered like 99.7% of the curve. So that's a lot, right? So anything beyond -3 and +3 is very little. The probability, the area is very tiny, right? In mathematics, we use negative infinity to positive infinity, but in practice is anything like beyond -4. From -4, imagine like 4 standard deviation. That's like almost like literally like entire curve, right? Not literally, but pretty much it, right? It's gonna be extend all the way out here, 4 standard deviation. The curve is gonna get really flat at the it kind of like lay on top of x-axis, right? So anything beyond like -4, less than -4, or bigger than +4, the area is very tiny. We don't care. Okay, so let's use this, and we're gonna calculate some values according to the empirical rules. Okay. Here's the I click a question, but you don't have to. Some of you, I don't know, you guys have I click a question. I want you to answer this, but just put in the chat box. Okay, put in the chat box. Maybe you don't have to do I click a question. Below is a model for the random variable X, which represent the height of the American males. What is the probability distribution with corresponding parameters? So I'm asking about distribution, right? Distribution. The distribution, so this is a normal curve. So distribution is normal, mu, comma, sigma. Can you fill in what is mu and what is sigma? By looking at the picture. If you do, put in the chat privately. Okay, privately. Anybody? So normal what? If I ask you what is the distribution of this curve, then you're supposed to answer like n and then parenthesis and plug in the value for mu and the value for sigma. So what is the values for mu, value for sigma? Okay, yeah. All right. Let's move on. Oh, we have two more questions, two little questions. Okay, suppose last night you sleep 11 hours. How many standard deviation from the mean are you? So 11 hours, where is, let me fill in the 95% and 98%. So 95% is 2 standard deviation. And we have 3.6, 10.4, 3.6, 10.4. And then last one is 3 standard deviation is 1.9 and 12.1. Okay, someone sleep 11 hours. So maybe between 10.4 and 12.1, right? 11 hours roughly here. So that's 11. 11 hours. Now you know the hours. They want you to calculate this, how many standard deviation away from the 7, from the mean. So say from here to here, I know it's 1 standard deviation, right? From here to here, I know that's 2. Right, so it's gonna be roughly between 2 standard deviation and 3, and between 2 and 3, right? Between 2 and 3. All right, so remember mu, so it's on the right, so it's gonna be mu plus what? I don't know how many standard deviations, so I'm gonna call it n. You can call it x if you want, okay? Times sigma equal 11. Right, and then now I can solve for n, right? I know mu is what? Mu is 7. N, I don't know, that's what I'm looking for. Standard deviation is that 1.7 equal 11. And then you can solve for n. Okay, you can solve for n. 1.7 times n equal 4. N equal 4 divided by 1.7 is roughly 2.35. So it makes sense, right? It's between 2 and 3 standard deviation. Okay, that makes sense. Can someone do 5? How about you guys do the second one, the last one, and then put your answer in the chat for me privately, to me, so other people cannot see it. All right, let's do it. You guys do it. Let me know what you got. Okay. All right, let's move on. The standard deviation is a useful yardstick for measuring how far a value falls from the mean. Right? So basically the same, the repeating the definition of standard deviation, right? How far are you from the mean, right? On average. Now we come to the new idea. Now, what if I ask you, can you tell me what is the area? Maybe I'll highlight in black. What is this area from here? Say from here. You know what? I'll highlight in yellow. So you calculate the standard deviation at 11 hours, right? And I ask you, can you tell me what is this area, the tiny little area here, from 11 hours to the right tail? Or I can ask you, what is the area from the left side all the way up to 11 hours, that in blue? Right? How do I know how much area are there? Well, in order to answer this question, you need something called the z-score. Right? In order to do z-score, we need the z standard score, right? So the z standard score, what it does is that it transforms your regular data set into a standardized data set. Right? So standard score is the distance between the observed value and the mean. Right? So basically, they just tell you the definition, basically to tell you the formula right here. It is the distance, the difference between the observation, the little data point, x1, x2, x3, and the mean divided by the standard deviation. Okay, so in the mathematics, if you have to know the notation, it's going to be z stand for standard score equal x, your observation, minus mu, that's population mean, divided by sigma, that's standard deviation, right? Remember this formula. Oh, I think I'm gonna give you the formula sheet. I think it's on there. You don't have to remember. But it's not that hard to remember anyway. Once you do enough homework, you remember automatically. Okay, so what I meant is that I'm gonna transform this curve right here into a standardized curve. Right, so let me do, so let's try this one. Score on a final in a course have approximately a bell-shaped distribution. The mean score was 70 points. So the mean score is 70 points. And the standard deviation was 10. So I'm just label stuff here. Right. And then on the x-axis, that's score, right? That's the exam, the final exam score. Suppose Rob, one of the students, had the score that was 2 standard deviation above the mean. 2 standard deviation above the mean. 1, 2. So here, right here at 90 points, 90 out of 100. That's pretty good. What was Rob's score? Right. Oh, I tell you the answer. What will Rob score? Right. So I know that he 2 standard deviation above the mean. So that means on the right of the mean. Then can you tell me what is the score of Rob? What his score? What should I do? What should I do? How do I figure out what the score here? What his score?
You multiply 2 by 10 and then add 70.
Yeah, very good. That's the same thing we did just earlier, right? Thank you. Don't be afraid to talk. So 70 plus 2 times 10, right? So 90 points, 90 score, 90 point, I'll say point, or score, whatever you want to use for the units. So that's the answer I highlight in blue. That's the answer that we try to answer. What can you say about the proportion of the student who score higher than Rob? what can you say about the proportion? What they're asking about the area, who score higher than him. So here he's right here, 90, higher than 90 is this part, right? Higher than 90 is that part, right? So can someone tell me what is from, what is this, what is the area in the, let me highlight in yellow, in the yellow area? Just approximately, can you tell me what is the area under the yellow part? I don't know, right? I don't know. And that's okay. If you don't know, that's okay. Because what we're gonna do is gonna look it up, right? We're gonna look it up. The reason we want to figure out what is the probability under the curve? Well, I'm sorry. In order to figure out what the probability under the curve or the area under the curve, we need to know what is the z-score, right? Why? Because once we have the z-score, we can look it up on table, right? Or we can use calculator or Google Sheet, which I'm going to show you later. But on the exam, at least on the exam, once I know the z-score right here, how z-score, I can project the z-score in the table and then find the probability, right, the area under the curve. So if I go back here, so the z-score is, I think we know this, what I'm going to do by hand anyway to see if it matched the answer. So remember the z is equal to x minus mu divided by sigma, right? That's the formula. X is 90. That's the observation, right, which is Rob. Minus mu is 70 divided by 10. 20 divided by 10 is 2. That's why it's 2 standard deviation from the mean, right? Which is 2. Now, that 2, now, instead of drawing on that curve earlier, now I can draw on the standardized curve. The standardized curve is n, the mean is 0, and the standard deviation is 1. Right? So the mean is 0, right in the middle is 0. Just listen to me now. I'll give you a few minutes to copy that down later. Okay. So the mean is 0, and the standard deviation is 2. 1, 2 right here. And when you look it up, when you look up on the table, it'll tell you the cumulative probability from left to right. When you look up 2 on z table, let's see, let's go down here. Z is 2, so basically 2.00, right? So 2.00 is right here. 0.9772, right? 0.9772. Let me go back here. 0.9772. When you look it up, what it does is calculate all the area from left all the way up to 2. The area all the way up to 2 under the curve. Okay. And if I want to know the one from the right, I want to know that little blue, the blue area. What do I do? You guys should know. What do I do? If the yellow is 0.9972, then the blue part is,
It's 1 minus 0.9772.
yeah, that's it. Which is very small, right? Which just makes sense. It has to be small, right? 1 minus 0.9772, which is 0.0228, roughly 2%. That's very small. 2%. So the area on the left, the area on the from left up to that point, you can look it up on the table, right? But if you want to calculate the right tail area, you have to take the complement meaning 1 subtract the area from the left, okay? So what can we say, what can you say about the proportion student who score higher than Rob? Well, roughly 2%, roughly, so we can say this. So according to this, we say roughly 2.28% of the student score higher than Rob. Wow, that's a very tough final exam. Only 2% is score higher than 90 points. Must be a rough final. Are you okay with this example? Yeah. Okay. If you have question, please ask. Okay, don't be shy. It's just 8 of us here. All right, so that's the reason why why we need the standardized standard score. So we can convert it into a standardized curve. So that curve right here, that standardized curve, where instead of normal, mu sigma, now mu is become 0, and then sigma become 1 for all standardized curve. For all standardized curve. All right, let's now I'm not gonna ask on the exam. I'm sorry, on the exam, you're gonna be able to use a table. But on the homework, you probably need to use the software. Okay, so that what I did, finding the probability. That's what we did. That's what we did recently. The z-score play a key role in how we will find the areas. We simply convert the endpoint of the interval of interest to the corresponding z-score. That's what we did. That's what I just did, right? Then use a table or computer or calculator to find the probability associated with the z-score. Okay. When we convert to the standardized z-score, the variable x is converted to standardized normal random variable z, which has the distribution. Maybe I'll put something here, n 0, 1. Right. So basically what we did was we convert this curve. Remember we have two of them. One is normal, what mean is 70, standard deviation is 10. And then we convert it to standardized, which is now n is, mean is 0, standard deviation is 1. And we can do that for every problem. As long as it's normal, we can do it for any problem using standard score. All right, cumulative proportion. I mentioned this earlier as well. So when you look up on the z table, it's always scanned from left to right up to that point, up to that value x. Right? To find, if you want to find something from the right, you have to take 1, subtract something from the area from the left. Okay, there's no way around it. Well, there's one way around it if you use R. Okay, so let's practice using the z table, because this is what we're going to use on your exam. I want you to find the probability where z is less than or equal to 1.22. Remember I showed you how to write the probability in notation like that? 1.22. So let me draw, I'm going to draw that curve just because. So because it's z, I'm going to denote 0, 1. Okay, 0, 1. Mu is, mean is 0, standard deviation is 1. Z, so here in the middle is 0 and 1.22 right there. And they want to find the probability is z is less than or equal to, that means I want this area. That means I want this area right here. Something less than 1.22, right? So all you have to do is look up on the z table, go down here, 1.22, let me erase that. 1.22 is right here. And then the last digit, the third one, is from the column. So 0.002, 1.22, and then right there. Okay, so 1.22 is roughly 0.88888, 88.88%. So when we look it up is 0.8888, which just makes sense, right? It has to be more than 50% because it's past that 0 point, right? 0 is right in the middle. What about P of Z is bigger or equal to 1.22? That means I want the blue area, right? So again, like Sean said earlier, we're just gonna subtract from 1. So 1 minus 0.8888. So it's equal to 0.11. 0.1112. Yeah, 0.112. Okay. So far, so good. Okay, not last one. Number 3, I want to find the probability is sandwiched between 1.58 and 2.24. So let me draw it out. You know, if you confuse, picture is the best way to go. You gotta draw it out, see what you're looking for. So again, because it's the standardized, mean is 0 in the middle, 1.55. I'm sorry, 1.58. 1.58. Oh, what time we done? Am I went over? Just let me finish this one. We finished, okay? And then 2.24. So I want something between. So that means this is the area I want, the one I highlight in green. Now in mathematics, if you want to find some function in between, you take what? You take the bigger function, subtract a smaller function, and then you got something in between, right? So that what I meant is I'm going to take the bigger function here, subtract a smaller function, and then I got the green function in between, right? So that means this one, if I want to rewrite the probability of Z between 1.58 and 2.24, then I want to take the probability of Z all the way from the left up to 2.24, which is Z is less than or 2.24. Subtract the blue arrow function, so which is P of Z is less than 1.58. Okay, so look it up, 2.24. 2.24. 2.24 right here. I see 0.9875. 0.9875. Subtract 1.58. 1.58. 1.58 all the way down there. Yep, it is 1.58. 0.9429. 0.9429. I hope no one have a negative probability. You cannot have a negative area, right? 0.9875, we almost done. Minus 0.9429, which is 0.0446. So roughly 4%. Oh no, something wrong. Oh no, something wrong. Oh no, nothing wrong. My picture is wrong. No, my answer is correct. My picture is wrong. I'm so sorry. Let me fix my picture. 1.5 should not be on the level 0. That's negative value. I am so sorry. It's been a long day. 1.58 right here. 1.58 should be on the right of 0, right? And then we have a tiny little green. It should be small, even smaller than this. I just have to show you some area. Okay. All right, that's it. And then we're going to continue